All right, so where does the lice minus lick come from? It's a little bit of a stretch, but there's the word lice minus licked, LKT. So the coefficient on T up in the exponent is the product of L times K, which might come into play. It will come into play. We know that we have an inflection value. I saw a news report that suggests we might have hit it. Let's hope so. So the graph is increasing most rapidly. The graph of population, not the graph of the derivative, is increasing most rapidly at L over 2, halfway between the floor and the ceiling, or halfway up to that maximum limit. So notice that's the Y value. You'll have to find the T value, and we'll do that in a couple of examples. What is the predicted population of Alaska in 2020? I'm not sure. Alaska. So we are looking at a differential equation, we're looking at a logistic growth curve. We are at lice minus lick. That's my L. That's the product of L times K. What is the predicted population of Alaska in 2020? Well, let's go ahead and graph it. O time if you can go into fraction mode by doing alpha F1. Alpha F1 will then display it as a fraction, numerator over denominator. If you have old notation, you better make sure you put that entire denominator in parentheses. Otherwise, it's going to take 895,598 divided by 1. I wonder why you did it. And then add that second term instead of divide by it. So make sure that whole denominator is in its own set of parentheses. If you're looking at a multi-part problem, oftentimes it is advantageous to type it into Y1 because you're going to calculate the population at 120, you're going to calculate maybe the derivative at 60, so it's going to be advantageous to have it typed in. Good. So, I'm going to set my window. I'm going to look at 200 years worth of Alaska's population growth. So I'm going to go 0 to 200, or I like to see my axis. So I went negative 10 to 200, counting by decades. Now, that top population is my limit. I could do a zoom 0 and let Ty figure out what the range is and open the window up according to the range. Or I can say, hey, that upper limit is 900,000. And I'll probably want to count by, I don't know, 10,000. And graph. And why is it not graph? Did I not turn the equation back on? Oh, yeah. So there's my population of Alaska curve. There's that logistic curve that we should have expected when we saw the lice minus lift equation. You should be able to see the inflection point. I can use this curve right in the graph window if I'm going to use 120, because 2020 is 120 years after 1900. And if 120 is in my graphing window, I can just do trace 120 years, and there's the population of Alaska in 2020. I could also do it from the home screen, second quick. Those of you with the old notation are going to do bars, y bars, function, y1 of, in parentheses, 120. Those of you with the shortcut can do alpha F4. So I'm going to label my answer with people. How fast was the population of Alaska changing in 1920, 1940, 1999? How fast? That's asking for a rate. That's asking for a derivative. Now, they don't, I have to look at the scoring rubric for this one. We're essentially being asked to find P prime of 120. Sorry, P prime of 20. P prime of 40. P prime of 99. I think you can just write that and then find it by doing n deriv on your calculator. If the calculator test, in fact, that has to be the answer. If it's a calculator test, they will not require you to take a derivative by hand. If it's a calculator test, I'm going to write this notation and then just write my answer. And I can do that from the home screen, Math 8. Those of you with the old notation, you're going to type y1, comma x, comma 20. Those of us with the new notation, type it in slightly different order. Alpha F1, oops, alpha F4, alpha F4. And x equals 20. Enter. What's my unit? The rate, dp dt, units of p over units of t, people per year. I can also do this from the home screen. So from the graph screen, I can go to the graph and I can trace, second trace, how about dy dx? Second trace 6. Those of you with the old notation, it might say n derivative, numeric derivative. And it wanted it also at year 60 and year 99. So I can type in 60. And there's the rate of change in 1960. 8,332.6269 people per year. Make sure you're giving me the dy dx value, not the y value. We haven't yet hit the inflection point. And then at 99, second trace dy dx. I actually prefer to do it from, if I've got it typed in, and that 99 is in my domain, is in my graphing window, I'm going to go ahead and I prefer to do it actually from the graph window. At x equals 99, 9,741.748 people per year. one baby was being born across midnight, apparently. Turn the knees up. Yeah. We're above the inflection value now. When was Alaska growing the fastest? And what was the population then? What's this question asking us for the inflection point? So C is an inflection point question. And I'm going to find it by, I know that the population is L over 2. I know the population is 895,598 over 2. That's the population. When is that happening? Let's let Ty help us out. Go to y equals. And I'm going to graph in y2, 895,598 divided by 2. Notice I showed that by just writing that equation on my paper. And then I went over and graphed it. Shazam. So apparently this graph is telling us to be softer. We musicians get that. Right? That's a softer symbol. Forte, is that the forte symbol? Okay. All right. So I'm going to now do second trace intersect. The first curve, enter. The second curve is the line, enter. The guess is a shameless plug for designer jeans, enter. And it tells us the intersection is 1982.765. And the population at that point was 447,799 people. Well, yeah, you can give me the date. It's like September of 1982. Right? So you can say 82.76 years after 1900, or you can say 1982.765, that's fine. What does the equation tell us about the population of Alaska in the long run? I'm going to take the limit. As t goes to infinity in the long run of 895,598 over 1 plus 71.57 e to the negative 0.516 t. And I'm going to say that that equals 895,598. Notice my notation. I've got the limit over there, and now I'm going to evaluate the limit by substituting in infinity. Now, e to the negative infinity could be written as e to the positive infinity in the denominator, but only in the denominator of that fraction, not of the factor. So what's 71 divided by e to the infinity? The whole denominator does not become 0. The denominator becomes 1 plus 0. So in other words, the limit is 895,598 people is the maximum population of Alaska. Hey Google, what's the population of Alaska? All right, we haven't hit the maximum, and I wonder if this trend is continued. Good question.
What is it?
790,000.
Oh, it's pretty close.
Oh, there you go. True. That's pretty close to the population that we found. That was the 1990 or the 2019 population. All right. Here we go. Sometimes that equation started you with the population function. We had to know logistic. We had to know that the numerator is the limit. We had to know that the exponent was L times K. In the next problem, they're going to start us with the differential equation. We have to understand that they are giving us Ky times L minus y. You have to understand that. Otherwise, you've got to go through that process of everything that we did yesterday that was so boring.
Not so, kind of.
Once I've identified that 100 is L, the carrying capacity for bears in the wildlife preserve, is that like wildlife jelly, is 100. Why? Because L is 100. What is the bear population when the population is growing the fastest? Go ahead and do that whole process that took us about 25 minutes yesterday. We did other stuff too. Or know that it happens at L over 2. It equals 100 divided by 2. In other words, it's 50 bears. What is the rate of change of the bear population when the population is growing the fastest? In this problem, the derivative rate is a function of p. We could do like minus lick and take the derivative, but if I did that, then I'd have to solve for t and substitute t in. Here, I just have to know that dp dt is equal to 0.008 p times 100 minus p. What is the rate of change when it is growing the fastest? Well, I know that that's 50 bears. 50 bears. Because question B is asking me for inflection point. And what's the rate at the inflection point? And what do you get, 20? 20 what? Good, units are important. Hey, boo-boo, let's label the answer. Raise your own time. So bears per year. Oh, bottom. Whoa, that's right. Bottom. Questions about that problem? So the population develops according to the logistic differential equation. Again, this is a real life AP question. Logistic is a BC topic only, not an AP topic. Pretty nice of them to tell you that this one is logistic. But boy, it doesn't look like it, right? We know that logistic is dy dt equals ky times L minus y. How can I put this one in this form? What? I don't feel like doing that whole process. factor, right? I've got to factor because I've got 1y in my differential equation. My logistic differential equation is of the format L minus 1y. So I've got to make this one minus 1p. So I'm going to factor out the 0.002. So once I factor out the 0.002, I get 0.002p times the quantity 0.2 divided by 0.002 minus p. Now I can identify L. I can identify K. So now I'm sitting here with dPdt equals 0.002p. 0.2 divided by 0.002 is 100. So A, B, and C are, once I've done that, are 0-minute questions. Right? Because the limit is L. It does not matter what that starting population, what that 0.5, 0.60, and 0.120 are. The limit is 100. In all cases, the limit is L. So now I'm going to go ahead and write my P of T equation. So question D asks me to sketch the solution curves. So I'm going to go ahead and write P of T equals lice minus lift. Lice is L. I, really 1. C, E, there's the lice, minus LK, 100, K is 0.002, T, here's my lice minus lift. Not so bad. Now I get to find C. So I'm going to find C by substituting in that 0.5. Um, 100 times 0.002 is negative 2/10. So if I substitute 0.5 in, the next one becomes 0. Cross multiply if you must. If I cross multiply, it becomes 5 times 1 plus C equals 100. Divide both sides by 5. And then divide or subtract 1. Your life will be easier if you understand that in a proportion, I can switch numbers on the diagonal. It's called the means exchange property. We've talked about it before. And that's 5/1. Numbers on the diagonal can change because of the multiplying and then dividing. So those could change places, and those could change places. Cross multiply and divide if you must. So now I get C equals 19. For part B, I get C equals 2/3. And then for part C, I get C equals 100 divided by 120, subtract 1. I get 1/6. I did that quickly. I want to free you up for some time. I did one calculation with you. So now let's go ahead and look at the graph. I'm going to graph those three equations. In A, C is 19. In B, C is positive 2/3. And, I'm sorry, in A, 19. In B, positive 2/3. In C, negative 1/6. So let's graph that. Y equals. I don't feel like typing over and over and over again. So I did my array business again. I did 100 divided by 1 plus C, but I put those three C values in brackets separated by commas. There's a trade-off. The trade-off is we don't get to see three different pretty colors. Sadly, it's all the same color. Let's set our window. For what? Bump this up. I'm going to go negative 10 to 100. I can always change that value. My Y min, I know that the floor is at 0. The maximum is 100. That's the L. But something funky is happening, so I'm going to change that to 200 at the max. And make that scale 10. And we graph. Here it comes. This is the one that's going to go through. Oh boy, did I have to turn it on? What I was thinking. Hey. So here's the curve that goes through 0, 5. And there's that logistic shape that we should expect. Here's the one that goes through 0, 60. There's that logistic curve that we should expect. Here's the curve that goes through 0, 120. Wait, 120? That's above the limit. The limit is an attractor. If I graph the slope field, think about what the slope field is going to look like. We're going to have dashes, and the dashes are all going to attract toward that 100. They're going to attract toward that horizontal asymptote from below. They're going to attract from the horizontal asymptote above. So the one that starts at 0, 120 is above the inflection value. It's above the limit, so it won't have an inflection value. And the first two are strictly increasing. The last one is strictly decreasing. All right, last problem. Lice minus lick. Let's look at that after we do this last thing. All right. So this question, if we're jotting notes about what this question is aimed at. Understanding how to go from the differential equation to the population equation, the lice minus lick. Understanding how to solve for C, given an initial condition. So in the equation, dp dt equals 0.001 p times the quantity 3000 minus p. There's my k value. There's my L value. So I can quickly, without going through all that stuff that we did yesterday, P of t is equal to lice minus lift. 1 plus C E to the L K minus LK T power. So I'm going to evaluate that for 0.50 to find the value of C. If my notation's not great there. How's this? When I evaluate at 0.50, that gives me this. I can solve. Switch the numbers on the diagonal, or cross multiply and divide. It's nice if they gave us 0, but if they didn't give us 0, we still have a little more work to do. Subtract 1, and I think I get 59 equals C. So now I know what P of t is equal to. Oops. I'm not going to put C there, and put the actual value of C. Blah. There. What's the size of the population when t equals 2? Find P of 2. Use your solution to find the number of days that have occurred when the flu is spreading the fastest. What am I looking for? Inflection point. And I know that the inflection point is going to happen at y equals, or p equals, 3,000 over 2. That's not a when answer. Well, I guess it kind of is. Well, it gets a little more specific. The number of days that have occurred. So I could say when the population hits 1,500 people, but that doesn't answer the how many days. So I do have to find the number of days. So, boom. I guess we could talk about whether you'd want to just put L and K in this general format, and then you could store the values for L and K. It saves you a little bit of typing. I don't know, because you know it's going to be on the test, but I know I'm looking at 3,000. One plus C was 59. E to the negative 3x. And I'm going to set y2 equal to 1,500. And I got to set my window. That K value is pretty large, so it's going to happen pretty quickly. So I don't think I need to see up to 100. I could be wrong. And I'm going to go ahead and set my max equal to 3,000. No danger of being above here, right? Because my LK was positive 3, which makes negative 3 in the exponent. Oh yeah. That's pretty rapid growth. The K being that steep makes that pretty rapid. So I could probably maybe even go to 5 as fast as that road. Oh wait. Never mind. That's bad logic there, blah. Well, we see the inflection point, I just don't see the curve very well. Go back to Wendy. There, now we'll see that shape that. Wait, what? All right. So I don't know.
What was your, Y max?
Did I not? Oh, it said 300. That was my issue. Yeah, no, that's good. I appreciate you. All right. So there's the curve as best as we need to see it. There's the 1500, and I just need to find out where they intersect. Second, trace, intersect. Curve 1, upper left corner, hit enter. Curve 2, upper left corner, hit enter. My guess, don't care. It is 1.359 days. All right. Humans at home, I'm about to pass out to my humans in the room the homework assignment associated with this lesson. It looks like a big package. You should have already done 3 of the problems last night for partial fractions. And the rest of it you might be able to finish in class.